In this video, we will discuss about the Bayes classifier. Now, this classifier is a fundamental classifier that has been developed in a machine learning domain. Now, all the other classifier that has been developed in the machine learning is based on the analysis of the Bayes classifier. So whenever we do the analysis of other classifier in the machine learning, you will see that we will base its analysis on the Bayes classifier. So this is very fundamental classifier in the machine learning domain that has been developed. So in this video, we will discuss about the motivation of the Bayes classifier. Then we will define how the Bayes classifier has been defined, and we will see the proof of optimality of the Bayes classifier. We say that the Bayes classifier is optimal such that it is giving a minimum possible error over the test data for all possible classifiers that you can develop. Now you might wonder that if it is giving you minimum possible error, then why at all develop other classifiers, just work with the Bayes classifier itself. So this is somewhat a theoretical classifier, we can't actually work on it, but we can base the analysis of the other classifier over the Bayes classifier. So these things will become clear slowly when we define the Bayes classifier and define the proof of optimality. So let's start the video. So please remember, in our supervised machine learning domain, we have two kinds of problem. One is classification problem and regression problem. In last videos, we have discussed the linear regression problem. Now we will discuss a classification problem. And the Bayes classifier is a very basic classifier that is defined over all possible classifier that has been developed in the machine learning domain. So the difference between classification and regression problem: in classification, the final output is a class label or a categorical output, or in a regression problem, the final output is a real value or a continuous output. So that's the only difference. So in a classification, it could be one of the class, and in a regression problem, the final output is a continuous or a real value. So let's see certain example. Let's say you are given a certain attributes or features of a certain person, and you want to predict that this particular person has a certain disease or not. So this is a disease prediction problem. Now here the final output is this disease column. Now given the attributes or given the features of a certain person, we need to output whether this person has a disease or not. So it's a kind of yes or no kind of output. Again, it's a categorical output. So that's why it is considered to be a classification example, and the person data could be represented using a certain set of attributes. So I am considering for example, I am considering only 3 attributes, which is age, heart rate and weight. You can also consider more attributes or more features, and together all such features and attributes represent certain person. Now given this person, you need to predict that whether this particular person has a certain disease or not. So it becomes a classification problem. Similarly, a regression problem could be seen as estimating a price of a house. Now price of a house is a continuous value. It could be real value. So this becomes a regression problem. So given a certain features or attributes of certain house, so here I am considering only 3 attributes. Let's say area of the house, bedrooms, number of bedrooms the house has, number of balconies it has, and given all these attributes, you are supposed to estimate the price of the house. So this becomes a regression problem because the final output of this particular problem is certain real value or a continuous value. We have already seen this. So the machine learning paradigm goes by this: you have a certain input, you develop a certain machine learning algorithm, and you have a certain output. So this machine learning algorithm could be seen as learning a certain function of input and outputting a certain output. So that's what machine learning algorithm does. It is learning certain function which is mapping input to output. But the problem is this function is usually unknown. Not usually, every time it's unknown. That's why you are learning a machine learning algorithm. Otherwise there is no need to learn the machine learning algorithm. You already have a function. So where there is a need of learning a machine learning algorithm, this function is unknown and you want to learn it through the training data. That's what the paradigm of the machine learning algorithm is. So if a feature vector, we represent it as a RD, so it's having a D features and it belongs to the R to the D. Then the function which is predicting house attributes or house features with the corresponding house price could be seen as a function which is taking input from the domain R to the D and outputting certain non-negative real value. So the domain is R to the D, the codomain is R plus. Similarly, for a disease prediction, the domain remains same. Think of it that a person is having a D attributes, and this D attributes is a feature vector that has been given to your machine learning algorithm. Now your machine learning algorithm will finally output yes or no. So it's kind of categorical output. So only codomain will change either in a regression problem or in a classification problem. So after we train a machine learning model on training data, what we do? We evaluate the machine learning algorithm on a certain test data to evaluate or to get some numerical quantity that indicates how good the machine learning model performs. Now this is what the revision that we have done. Now in a machine learning algorithm, the task is not only important. The distribution from which your training data or test data comes is also very important. So we assume that your training data and test data is coming from certain unknown distribution. So this word is very important. This distribution is unknown, and we assume that it is coming from a certain unknown distribution. So right now we have defined a machine learning algorithm, or we have classified a machine learning algorithm mostly basis on the task it is performing. So not only the task of machine learning algorithm is important, so it is a regression problem and classification problem. That's not suffice, is it? We also have to consider from where this training data or test data comes. So the data distribution of the training or test data is very important. So we will see why it is very important. So machine learning models trained on a same task but on a different data distribution are actually incomparable. So let's say you are training a certain machine learning model and it is predicting a certain person has a disease or not. Now this particular machine learning model is, let's say, expected to predict a person disease for a person data coming from Indian people. Now let's say there is another machine learning model which is predicting a person is having a disease or not for African people. So now you have two different machine learning models and you want to compare them. This is not very fair comparison because the inherent data distribution from which the training or test data comes for both the machine learning models are very different. One is working for Indian people and other is working for African people. So we need to assume it. Even let's say your machine learning model is very general, it is predicting a certain person has a disease or not for every kind of person. Now that also the distribution is very important. So how much proportion of the data is coming from the Indian people, how much is coming from the American people, how much is coming from the African people. This distribution is very crucial. So we can't disassociate the data distribution from which the training and test data comes for the machine learning algorithm and only focus on the machine learning algorithm functionality. We need to also consider the data distribution from which the data is coming for the machine learning model. Why? Because two different machine learning algorithms are performing the same task, but the data for these two different machine learning algorithms are coming from a different distribution. So we can't actually compare these two machine learning algorithms because its training data and test data are coming from a different distributions. So that's why machine learning task is always assumed to be solved for a data coming from a certain underlying distribution. And not only that, this underlying distribution is usually unknown. So that's the primary assumption that we make, that there is certain unknown distribution for which the training and test data is coming and your machine learning algorithm is trained over that, and the error is also evaluated on the data coming from the same distribution. So it will go like this. So there is unknown distribution, so that I have indicated using this particular blue color cloud. This is a certain, let's say, data distribution, and let's say think of it as a black box. So you are querying this data distribution, and for each query it is outputting certain data point. That's how it is working. You are querying this data distribution, and for each query it is taking giving you certain data point. So this will work like this. So you ask for a data point n times, and you create certain training set. So you will get n data points. So after creating this training dataset, you train your model over this training dataset. So now you want to evaluate how your model is performing. So you query the same distribution for a test dataset. So let's say now you are querying m times, and you will get a m data points to get a test dataset. You will form a test dataset from this, and you evaluate the error on this test dataset. So please imagine it like this, that there is certain unknown distribution. You are querying this distribution and you are obtaining your training and test datasets. So you have to be comfortable with this particular kind of black box way of imagining it and obtaining the training and test datasets. And this distribution is usually unknown to you. So what is the, let's say data point for your data set? So in the training data, what you call it as a data point? So data point is nothing but the feature vector plus its label. So this is your feature vector. I have indicated using this particular blue color and corresponding label. So this pair, feature vector plus corresponding label, will be called as a data point. You query n times, so you get n data points, and you query m times, so you get m data points. N data points are for the training, m data points are for the testing. Okay, so data point is a certain row of the input table. Okay, we consider this as a random because it is coming out of certain distribution which is unknown. So we consider it as a random. So please be comfortable with this notation. We will work this data point as a certain feature vector and its corresponding label, but both of them are a random and they are coming out of certain distribution. So now I will define certain notation that I will refer throughout these videos. So please be comfortable with these notations. So whenever I refer a uppercase notation, I will usually refer a certain random variable. So X is a random feature vector. So this could be seen as this particular row. This I have indicated using this particular orange color is a certain vector, and it consists of 3 features. Now this vector itself is a random, and each of these entry of this vector is also a random. So we will refer it like this, that X is a random feature vector and it consists of D features in general, and capital X superscript 1, capital X superscript 2 up till capital X superscript D are also a random features. So X is a random feature vector which is made by D random variable. So are you okay with this notation? You have to be comfortable with this notation. Similarly, Y is also a random output label. So all of them are jointly distributed. Okay. So capital X superscript 1, capital X superscript 2 and capital X superscript D are jointly distributed and they are forming certain random feature vector X. And similarly, Y is also jointly distributed with X. Okay. Now you query your unknown data distribution, you will get a certain pair of X and Y. Random feature vector plus corresponding label. So that's how we will work with it. Okay. So XY forms the input data point. So whenever I refer a lowercase notation, I will refer the corresponding value taken by the random variable. So for example, small x is a corresponding value taken by the random feature vector X, and this small x is made by this particular D dimensional feature vector. So small x superscript 1, small x superscript 2 up till small x superscript D. All of them are indicating a specific value taken by each of these features. So whenever I refer a features as a random variable, I will use a capital letter. Whenever I refer a specific value taken by this feature, I will use a small letter. Similarly for a feature vector as well, and similarly for the output value as well. So small y is a value taken by the random variable y. So this is what I will work with it. So one more assumption we will make, that there are noisy labels in the training data. So for a same x, 2 different output labels are possible. So let's say there is certain unknown distribution, you are querying one time and you get a pair small x and small y subscript 1. You query again and you might get a same x. So you will get a same small x, but the corresponding label is different, small y2. Here y1 and y2 are different, but x is same. So that might be possible, and we work with this particular kind of scenario. And this is very realistic scenario. Please imagine, let's say you are working with the house price prediction problem. So you have a certain data of various houses. Now it could happen that there could be 2 different feature vectors which have a same attributes. All the attributes are same. but the corresponding selling price is different. It could be very much possible. It's very realistic scenario. So we can't say that there are two houses which are having all attributes as same, but still their selling price is different. Similarly, let's say you can even disease prediction also have this kind of scenario, that there could be two different persons. They are having same characteristics. All the features for these two different persons are same, but the corresponding disease condition is different. One is having a disease, another is not having a disease. So this kind of possibility is there. So with how much probability one will have a disease, how much probability one will not have a disease, will be determined by the underlying data distribution on which we are working with it. So it is all random now. Please be comfortable with this kind of analysis. So furthermore, we will assume that our main problem is a binary classification problem, two-class problem. So let's say you have a small x, small y as a data point. So here small y will be either 0 or 1. So 0 corresponding to the one class and 1 corresponds to the other class. So you only have a two classes, and y is taking value either 0 or it is taking value 1. So this is the setup we will work on it. Okay. So I will explain why I am only considering two class problem and why not multi-class problem. Actually, multi-class problem is just an extension of the two class problem with slightly added complexity. So I will just touch upon it. Let's say you have a k classes. So what you can do for the k class classification, you can create a k binary classifiers, and this ith classifier will indicate whether the data point belongs to ith or not. So this is a reasonable model, but you might encounter two problems. You have a k classifiers and you give a certain data point, but no classifier says that this data points belongs to that class. So which class label you will assign to this particular data point? So that is one problem. Another problem is what if there are multiple classifiers which says that this particular data point is belonging to this class? So you need to come out with certain strategies to deal with this kind of problem. But in general, you can create k binary classifiers and you can solve the multi-class problem. So binary classification is a very specific case, and it is a simple case. So we will work on only the binary classification. So we will deal with the scenario of a multiple classes later. So now for a two class classification problem, every function which is mapping a given feature vector to 0 or 1 is a certain classifier. So let's say mathematically if h is a classifier, so how you can denote it? H could be seen as a certain function. We have seen that classifier or a machine learning algorithm is a certain function only, whose domain is what? R to the d, which is because it is taking a d-dimensional feature vector in, it is outputting what? The codomain or a range is 0 and 1. So it is outputting either 0 or 1. So H is a classifier or H is a binary classifier. It will be mathematically represented by this. The domain is R to the D and the codomain is 0, 1. Okay. Now we are interested in certain classifier which is optimal or best in some sense. Not good, best in some sense. So I will modify this word good to best now. We are interested in best classifier. Now let us mathematically define the underlying unknown data distribution that we have assumed. So let's say small f subscript I is a class conditional density for a feature vector of class I. Now class could be either 0 and 1. So we are working with two class conditional density, small f0 and small f1. Okay. Now this is a class conditional density. So please know your features are coming from R to the D. Okay. Now this class conditional density actually indicates that probability of feature vector x with label I. So now let's say you have queried it and you are observing the label y equal to I. Now here please know the I belongs to either 0 or 1. So we are only working with the binary classification. So fi of x indicates the probability of feature vector x with class label I. More specifically, probability of x given y equal to I. So there is slight technicality involved. Class conditional density does not directly translate to the probability. If you have a discrete random variable, then the class conditional probability or class conditional mass function directly translates to the probability. But in case of continuous random variable, class conditional density will be proportional to its probability. So there is no direct analogy, but for the analysis you can relate it like that the higher the class conditional density, the higher the probability of random variable x given the class label I. So please relate it like that. The exact technicality is not that much important. The intuition behind it is more important. So please know this x is a certain random feature vector, and it consists of a d features, capital X superscript 1, capital X superscript d. So you have a d random variables, and the joint density conditioned on the class label I corresponds to the class conditional density. So let's try to geometrically represent for a very simple case scenario when you have only two features. So the class conditional density could be represented using the Cartesian coordinate. So let's say this class conditional density for both the classes are disjoint and linearly separable. So one of the scenario will look like this, that let's say class conditional density for a class label 1 is here, and class conditional density for class label 2 is here. Now this particular region indicates what? In the pink region, the class conditional density corresponding to the class 1 is non-zero, and the green region indicates the class conditional density corresponding to the class 2 is non-zero. For all other region, class conditional density for a class 2 is 0 if the region does not belongs to the green region. Similarly, for a class conditional density corresponding to the class label 1, if the region does not belongs to the pink region, the corresponding class conditional density is 0. So that's how I have represented this class conditional density. Hopefully you are okay with it. So the property about this particular distribution is the distribution is linearly separable. So I can draw a certain line such that both the class conditional density are nicely be separable. Now there could be other case that let's say it's not linearly separable, but still they are disjoint. So still these two class conditional densities are disjoint. So you can see it like this, that this particular pink region and green region are disjoint but not linearly separable. Still you can draw a certain curve which is separating both of them, but they are not linearly separable. This curve is not linear. Okay, both the densities are disjoint. So the other case is they are overlapping. So please, it need not happen that your class conditional density are disjoint. It can also happen that they are overlapping. So the pink region is overlapping with the green region. So what does this say? There are certain axes which I will denote using this particular orange region. Whatever the axes are in orange region, they might have two different class values, and that's the assumption that we are working on it. There is certain feature vector, it can also have two different values. So all such feature vectors in this particular orange region might have two different class labels. By what probability, which probability it will have a one class, which probability it will have another class, depends on the underlying probability distribution that we have assumed, but it's possible that it could have two different class values. So classifier does what? It is outputting certain class label given the feature vector. Now you want a certain classifier which is misclassifying the given pattern with the least possible probability. So that's how you want to define a classifier, and let's call this optimal classifier. So first let's define the class conditional density and original data distribution using certain notations. So let me define certain posterior probability function as a probability of class value I given x. So please remember always that I is either 0 or 1. So we are working with binary classification problem. Now qi of x, I will say that probability of class is equal to I given x. In another way you want to denote it probability of y equal to I given x. Both of them are same thing. So I call it qi of x. Now I define a certain classifier. So what does classifier do? Given x, either it will output 0 or 1. So let's say if q0 of x is more than q1 of x, then your classifier is outputting 0. Otherwise it will output 1. So this is very obvious and intuitive classifier that you have defined. So what is this qi of x? It is a conditional probability of y equal to I given x. So q0 of x is what? conditional probability of y equal to 0 given x, and q1 of x is conditional probability of y equal to 1 given x. So you have defined a certain classifier using the QIs. Okay. Now here I have used the word posterior probability. Why I am calling this as a posterior probability, it will become clear in a few slides, so please hold on. I will also define something called as a prior probability also. So prior probability is probability of y equal to I. So there is not a conditional probability, this is just a marginal probability of probability y equal to y. So P0 is probability of y equal to 0 and P1 is probability of y equal to 1. So I will say that. Now this particular Qi of x, let me try to denote it using the Bayes theorem. So Qi of x is this particular quantity. Please remember it's a probability of y equal to I given x. This is nothing but Qi of x. Now how I have represented Qi of x? This is same as probability of x given y equal to I multiplied by probability of y equal to I. In denominator there is a certain z. Now what does this z is? Z is a probability of x given y equal to 0 multiplied by probability of y equal to 0 plus probability of x given y equal to 1 multiplied by probability of y equal to 1. So please know this z does not depends on the class label I. So this becomes certain constant. Certain constant what? It's not constant for all possible x, but for a fixed x it is a constant. And in LHS you are analyzing for the fixed x. So this particular Qi of x is analyzed for a fixed x. So given a x, your probability is being determined, and for a given x, this z becomes a constant. This z is this particular quantity. Hopefully you remember the Bayes theorem from the probability lectures. So z is a certain constant and it does not depend on I. That's what I have also mentioned earlier, that it is a certain constant given x. So given x it becomes a constant and it does not depend on I. Please remember from the probability discussion, this probability is nothing but the marginal probability of x is occurring. So for a given x, this marginal probability should become a constant. So that's why this z is also a constant. So you need to remember our discussion of a Bayes theorem from the probability lecture. So please know this particular equation that I am indicating using this pink color. Let's denote this equation in terms of Qi and class conditional that we have defined it earlier. So please know this LHS is a Qi of x. The first term in the numerator of the RHS is the class conditional density only. So let's represent it using that. So Qi of x is equal to Fi of x multiplied by Pi given z. Please know Pi is nothing but this probability, prior probability of y equal to I. That's how I have defined it. So Qi of x could be represented as a Fi of x multiplied by Pi given z. Now your classifier that you have developed is comparing the Qi's. Please remember this was the classifier that you have developed. In this classifier you are comparing the Qi's. Now I am saying that Qi is nothing but Fi of x multiplied by Pi divided by certain constant z that does not depend on the class label. So I can ignore that constant and I just compare the numerator only. So that's what I will do. I will only compare the numerator, that f0 of x multiplied by p0, if it is greater or equal to f1 of x multiplied by p1, then it is class 0, otherwise class 1. And this kind of classifier I will call it as a Bayes classifier. Ultimately I am comparing the Qi only, but now Qi is just Fi of x multiplied by Pi divided by z. Z is not depending on I, so I can just compare the numerator. So this classifier we'll call it as a Bayes class. So now let me explain the meaning of Fi and Qi's once again. So Qi of x is given by this particular equation. I want to write this equation in terms of probability first. So Qi of x is what? Probability of y is taking a class label I given the x has occurred is equal to Fi is what? Probability of x is occurring given the y is I. So it's a class conditional density. And Pi is what? Probability of y is taking value I. Now please know this is a Bayes theorem, and in LHS this quantity we refer it as a posterior probability. In RHS the numerator, this conditional probability we refer it as a class conditional probability, and this particular quantity we refer it as a prior probability. So ultimately we are interested in the probability of certain class label occurring. Now if we did not have any evidence, so we did not see a feature vector at all, then what is the probability of certain classes occurring? So we call it as a prior probability that does not involve the conditional probability at all. So this prior probability is probability of the class label is having a value I. So that's why it is a prior. Now once you observe a certain evidence, that means you have observed a certain feature vector X has come. Now you are interested in the probability of the class label. So we call it as a posterior. So that is a conditional probability of y equal to I given the certain feature vector X has occurred. And the class conditional probability means you are interested in the probability of the feature vector itself, but given the class label is I. So that's the class conditional. So these terms will be frequently used throughout the course: class conditional probability, prior probability, posterior probability. You have to be aware and comfortable with these particular terms. What is the class conditional probability, what is the prior probability, and what is the posterior probability. Okay, so probability of y equal to I given X is a posterior, prior is only probability of y equal to I, and posterior class conditional is a probability of feature vector given the class label is I. So now let's prove the optimality of the Bayes classifier. So just remember the Bayes classifier that we have defined. It is outputting a class label 0 if f0 of x multiplied by p0 it is greater or equal to f1x multiplied by p1. Otherwise it will output the class label 1. So now I want to prove that this classifier is a Bayes classifier. And please know how I have defined this Bayes classifier. It is ultimately comparing the posterior probability only. So given a class, given a feature vector x, if the probability for the class label 0 is higher, then you classify it as a 0. If the class label 1 is higher, then you classify it as a 1. That's a very intuitive and obvious way to define a certain classifier. Whichever class has a higher posterior probability, given you have observed a certain feature vector, you assign that feature vector to that particular class. That's a very obvious and intuitive way to define a classifier. And that classifier we call it as a Bayes classifier. Slight technicality is instead of comparing the posteriors, we just compare the FIX multiplied by PI. So hopefully you are comfortable with the Bayes classifier. Now I say that this particular classifier, which is very obvious classifier that we have defined, is a optimal classifier. That means no other classifier that you could develop beats this classifier. And optimality in sense of what? In sense of error that is being made by this particular classifier. So let's prove this particular optimality. Now let H prime be any classifier. It need not be Bayes classifier, but any classifier. So what does classifier does? Given X, it is outputting either 0 or 1. So for all such X for which it is outputting 0, I am defining a certain set which is capital R subscript 0 of H prime. So this set is a set consisting of all such feature vectors. They are being classified as the class label 0. Similarly, R1 of H prime is what? Set of all feature vectors that are being classified as a class 1 by this particular classifier H prime. So hopefully you are comfortable with capital R subscript 0 and capital R subscript 1. These are certain sets I am defining given your classifier H prime. Okay. Now you need to observe two properties of capital R subscript 0 and capital R subscript 1. First of all, these two sets are disjoint. So if there is certain X that is being classified as a 0, that X will not be classified as a 1. Obviously, this is the definition of the classifier. You give certain X, either you classify it as a 0 or 1. So this is one property that these two sets are disjoint. The other property is the union. If you take a union of both these sets, you will get all such possible feature vectors. So obviously, any feature vector will be either classified as 0 or 1, right? So it will be either in one of the set, and you union both of these sets, then it will be entire input feature space. So these two properties are very crucial properties of capital R subscript 0 and capital R subscript 1. So in terms of probability discussion, what we can say that they are forming a partition of the feature space. Partition means what? They are not overlapping, disjoint, and the union of it are covering all feature space. And as you change H prime, instead of H prime, if you put H double prime, still you will get a different set, but you will get a different partition. You take H triple prime, you will get a different partition. Likewise. So please be comfortable with the sets I am defining. So now I am interested into the classification error that is being made by this H prime. So in terms of probability, how you can define this classification error? So remember, there is certain unknown data distribution, you are querying it and you are obtaining certain x and y. Okay, so now let's say this x that you are querying, if it is belonging to R0 but it has actual class label 1, then there is a error. And let's say you are querying it, and if it is falling into the R1 but it has an actual class label 0, then there is also error. So this particular probability can be written as a sum of two probability, that x is falling into the R0 but it has actual class label 1, plus probability of x is falling into the R1 but it has actual class label 0. Now please know, there could be certain instances where x is falling into the R0 but it has actual class label 0, and x is falling into the R1 but it has actual class label 1. In that case there will be no error. So I am not considering those cases. I am only considering when there is an error. So only two term will be there. So furthermore, at most one term will become active. So whenever you are querying it, x will either fall into R0 or R1. So at most one term will become active, and that too, whenever this x is being classified correctly, that term will become not active. If it is classified incorrectly, that term will become active. So this is summation of these two probability, and please know this is a joint probability. Okay, so can I write this joint probability using the multiplication rule? So this is what I have written in terms of multiplication rule. Now please know, this particular blue quantities are nothing but the prior probabilities, so they could be easily replaced. Now this conditional probability could be also represented as a class conditional probability. So this conditional probability is the probability of x in R0 given y equal to 1. So in terms of class conditional probability, how I can write it? This probability is over all possible x's over R0. So that means I am integrating the class conditional probability over R0. So that's what it is. This orange term becomes integration over R0, the class conditional probability. This is the probability that x belonging to R0 given y equal to 1. That is just integration over R0 class conditional probability, right? And please remember, what was the class conditional probability? It was probability of x occurring given the class label is 1. Now we are considering all possible feature vectors in R0, so you are integrating it over R0, right? Similarly, the second term becomes integration over R1 class conditional probability for a class 0, right? So now replace this quantity into the earlier equation. So this particular classification error becomes P1 times integration over R0 f1 of x, P0 times integration over R1 f0 of x. So please know, I am considering all possible x's, and this axis either will fall into R0 or it will fall into R1. And only one of the term will become active in these two terms, either the blue term or the pink term. Only one of the term will become active. So if x is in R1, then orange term will become active, or if x is in R0, then the blue term will become active. Only one of the term will become active. So either you are summing P1 F1 or you are summing P0 F0, depending on in which class the x is being classified by H prime. So that's what I have written. For each x, we either add P0 F0 or P1 F1 in this integral. Which term we will add depends on the class in which this x will be classified by your classifier H prime. So this H prime will determine which term I will add for the feature vector x. Okay. Now for a Bayes classifier, what I do? If P0 F0, if it is more than P1 F1, then I classify it as a class 0. Otherwise, I classify it as a class 1. That's what I do. That's the definition of the Bayes classifier. Okay. So in this particular summation, I am only considering the minimum value for a Bayes classifier. Okay. If I am classifying a certain feature vector as a class 1, that means P1 F1 is higher than the P0 F0. So P0 F0 will be added in the error terms of Bayes classifier, and that will be least than the P1 F1. Similarly, if P0 F0 is higher, then I classify it as a 0, but P1 F1 will be added in this summation. So this error will get minimized, right? Because I am only considering a minimum quantity for all possible x's. So error for a Bayes classifier will be indicated by this, and Bayes classifier will assign a class to a feature vector x such that this error integral will minimize. So this proves the optimality of Bayes classifier, right? Because it is picking a class in such a way that this error integral gets minimized, or it is an optimal classifier in such a way that it is making a minimum possible error over all possible classifiers that you can develop for this particular data distribution. So that's why Bayes classifier is optimal classifier. Let's see now different cases of class conditional densities. What will be the actual error of the Bayes classifier? So please know R1 is what in this particular figure. Now consider only left hand side of the figure. So R1 is what? It is a set of feature vector which is being classified as a class 1. So Bayes classifier will classify entire this particular red region as R1 and entire this green region is, so let's say class 2 is same as class 0, so it is R0. Okay, so these two are the regions that has been defined by the Bayes classifier. All such feature vectors in this particular red region will be classified as class 1. All such feature vector in this green region will be classified as class 2. Now what will be the error term? For all such feature vectors in this particular red region, I am adding which term? P0, F0. But F0 corresponding to this red region is 0. And similarly, F1 corresponding to the green region is 0. That's why the term that you are adding, please know, in the Bayes classifier, you are adding either P1 F1 or P0 F0. But for all such feature vectors in the red region, F0 is 0. Similarly, all such feature vectors in this green region, F1 is 0. So that's why Bayes classifier error for this particular class conditional densities is 0. Here error will be 0 for Bayes classifier. Similarly, here also error will be 0. For all such feature vectors in this particular pink region, F0 will be 0. And so for all such feature vectors in this particular green region, F1 will be 0. This pink region corresponding to the R1, the green region corresponding to the R0. So the error for this Bayes classifier is again what? It is 0. So when the class conditional densities are overlapping, error of the Bayes classifier is non-zero. That is this case. So here, for all such feature vectors in this particular pink region, F0 is 0. That is agreed. For all such feature vectors in this particular green region, F1 is 0. That is all agreed. So for all such feature vectors which is not in overlapping region, the error will be 0. But there are certain feature vectors which is in this particular orange region, which can have either class label 1 or 2. So depending on which class has a higher probability, your Bayes classifier will output that class. So there will be certain non-zero error that will be encountered by the feature vector in the orange region by the Bayes classifier. So here error will be greater than 0. So we have proved what? We have proved that Bayes classifier is optimal classifier. That means it is obtaining a minimum possible classification error over all possible classifiers that you can develop. Now please know this error we are analyzing based on certain assumed data distribution. We assume that data is coming out of certain data distribution and on which we are analyzing the error. Okay. So please know in the classification functionality only, what does Bayes classifier compares? P0 F0 and P1 F1, right? These probabilities are just the probabilities of this unknown distribution only, right? We don't know. So that's why it is using the probabilities of this unknown distribution and then it is classifying a given feature vector. So it is a optimal classifier. It is obtaining a minimum possible classification error, but it is using a probabilities of certain unknown data distribution, which we generally don't know. So we have analyzed the classification error of the Bayes classifier in such a way that it is a optimal, it is a minimum possible error among all possible classifiers. But to implement the Bayes classifier, you need to know the actual class conditional density and the prior probability, which is generally not known, which is unknown because the data distribution from which your data is coming is unknown. That's what we have assumed. So that's why Bayes classifier is optimal classifier. It is obtaining a minimum possible classification error, but we can't implement it. So Bayes classifier is somewhat a theoretical classifier, which indicates that you can't obtain a classifier which is having a lesser error than the error of Bayes classifier. But the problem with the Bayes classifier is we can't implement it, because the functionality of Bayes classifier itself use the probabilities of certain unknown distribution. That's why you can't implement this Bayes classifier. So generally we estimated this particular probability from the training data. So naive Bayes is one such algorithm which is estimating this particular probabilities through the training data. Now whenever you do the estimation, the probabilities need not be correct. So that's why whatever the classifiers that has been developed which are estimating these probabilities need not be optimal. But since that's the only possibilities, and you have to estimate it through the training data, so we work with these classifiers. So you develop any other classifier, the error for this classifier will never be lesser than the Bayes classifier. Bayes classifier will always have a lesser error than this particular classifier. But the problem is Bayes classifier you can't implement it, because it is using the probabilities of certain unknown distribution. To estimate these probabilities, you need to use the training data, and one such algorithm is a naive Bayes. So naive Bayes is not optimal, Bayes classifier is optimal. So thank you very much for watching this video. We will stop this video now, and hopefully you understood the reasoning behind the Bayes classifier, why we have defined the Bayes classifier, why we have defined its term, why we have proved its optimality. Because we will define many classifiers, and the analysis for this classifier will be based on this particular Bayes classifier. So this Bayes classifier is a motivating classifier for all such classifiers that we are going to see next. So thank you very much for watching this video, and we will meet you in the next video.